First time ever in Tibet, I was just excited because I had been brought up on adventure tales of Edmund Hillary climbing Mount Everest and the Mallory expedition being lost on Mount Everest. And here was the chance to come to see the Himalaya and Tibet for myself, and not just travelling, but travelling with a purpose and the chance to actually do science. It's beautiful Tibet. There are the small terraces with the wheat or barley that's ready to be harvested, and people working over there on the other side of the river. The Yarlung Zangpo River rushing down. Big rapids right here. Lots of nice deformed rocks around us. So it's a good place. It's a good place for geologists. That's hotter coming out of the source than we can feel in the water, okay? It may be that
Geophysicist Simon Klemperer is leading an unusual geologic expedition across the vast Tibetan plateau. With geologists from the US and China, Simon's group is searching for hot springs, as many as they can find across Tibet.
Yeah, so there's definitely atmosphere.
At each spring, the group takes samples of the water and gases bubbling up. By analyzing these in the lab, they hope to find out where the springs come from deep below. Down there, two gigantic tectonic plates crashed together about 50 million years ago. Ever since then, the Indian plate has been sliding or subducting beneath the Asian plate, thrusting up the Himalaya and the Tibetan plateau. But in one of geology's great mysteries, no one knows what the collision zone looks like.
When we first came here, there was a lot of debate about the boundary between India and Asia.
Did the Indian plate stop under the Himalaya? Did it slide all the way under Tibet? 25 years ago, no one knew. But Simon and his colleagues made a breakthrough using seismic techniques.
In 1992, we collected the first reflection profile in Tibet, and we were able to show through seismology that India dipped at a low angle beneath Tibet, but we still left open the question of how far north did India project beneath the Tibetan plateau.
We'll probably do the water sampling at the outlet down there and do the gas sampling right here.
Okay.
Why the interest in where the plates are below the plateau? For one thing, this plate collision has created Earth's highest and largest geologic structure, the Himalaya and the Tibetan plateau combined. It is Earth's #1 classic mountain building example. As this massive block of rock rose up, it changed the climate of the entire Earth. It created the Great Indian Monsoon, which affects millions of people each time it sweeps across Asia. The Tibetan Plateau and the Himalaya are also the source of many great rivers, which supply water to billions of people in India, Bangladesh, and China. The colliding plates below have another huge impact on the region's people. Massive, deadly earthquakes, like the Gorkha quake in Nepal in 2015. It is critical, then, that Earth scientists fully understand the collision of plates below. Yet, one of the collision's fundamental traits remains unknown: its location. This drove Simon Klemperer to resort to a radically different approach in finding the elusive plates.
This year's experiment was designed in an entirely new way. Instead of using seismology to try and track India as it extends north beneath Tibet, we're going to try and look for a geochemical signature beneath the Tibetan plateau. Right, okay. So I'm going to close this off now. And now I'm going to try and fill this up with gas.
That signature is written in the gases and water of Tibet's many hot springs. By reading that signature in the lab, the scientists will get a surprisingly detailed glimpse into the Earth's hidden depths.
The chemistry can tell you a lot about the source of the water. So if the water is very, very clean, it's probably sourced from rainfall. Whereas some of the fluids in hot springs can come from very, very deep, like deep as in the mantle.
One more try.
And in the Tibetan plateau, that means possibly 70 kilometers or more. By the chemical composition of the water, we can tell what percent of the fluid might come from the mantle.
The mantle is the Earth's second layer down, lying below the rocky crust.
You know, what I think's almost most bizarre about this process is that the bubbles that are coming out of the spring, some of that gas may have come from 70 kilometers or 100 kilometers below us, which is what we're going to find out when we analyze this in the lab. Okay, this is our first sample, and it's great.
The gas is mostly carbon dioxide, but it carries a certain noble gas that the scientists are most interested in: helium. If the ratio of certain helium isotopes, helium-3 and helium-4, are above a specific number, then the hot spring is thought to start in the mantle. If not, then the hot spring starts in the crust. Simon's assumption is that a crust sample could be from the Indian or Asian plate, but a mantle sample should be to the north of the collision zone, from the mantle of the Asian plate.
69.
Taking samples at many hot springs should tell Simon where the Indian plate ends below Tibet. Besides gas samples, the scientists also take samples of the spring water itself. With this, they can measure cations and anions, and elements like sulfur, carbon, and strontium. These can reveal important new details of the hidden depths below Tibet, like earthquake faults, magma pools, and reservoirs of hot water. The scientists had only been given a few weeks to do their fieldwork. Yet Simon and his group ended up collecting over 80 copper tubes of gas and water, and dozens of samples in other containers. A huge success. The samples were sent to labs in the United States and China.
So far, so good.
It takes months to get the results, and possibly the long-awaited answer to the question: where are the colliding tectonic plates below the Tibetan plateau?